Thank you, Kay. Hello, everybody. So yeah, as Kay said, I work in a group called the Infomatics Lab. I've worked in the Met Office for about 7 years now. My background is in technology. I used to work in kind of tech support area and kind of IT infrastructure. But a lot of what we do within our group is around being a multidisciplinary kind of research group, if you like. So we spend all of our time researching new technologies, new science, new kind of design, and doing that as a group of technologists, scientists, and designers. But an important thing to note about that is that, we're a small team of 10 with people from different backgrounds, but we don't come in and own a problem that we're trying to solve, right? So just because my background is IT infrastructure doesn't mean that I own all the IT infrastructure and nobody else gets to do any IT infrastructure. The idea is that we're kind of sharing knowledge and sharing experience within the group, and it means that we come out with some really interesting and novel ways of doing things. So our team's currency is basically prototypes. So we build things to try and demonstrate some new piece of learning, some new piece of knowledge that will help the Met Office kind of on the 3 to 5 year timescale. So is there some new piece of technology that's on the horizon? Is there some new mathematical technique, whether it's machine learning or whether it's a piece of tech like virtual reality or anything along those lines? We kind of pick up that thing and give it a good test drive. We'll come up with a project based on feedback internally within the Met Office into what people are struggling with, and then build some real tangible thing that people can touch and feel and understand in order for us to communicate whether something is useful or not. And it often means that you start with something that's really hyped and really exciting and everybody's all mad about, and you pick it up, you find some internal use case, and that example makes use of that technology or that technique, but it's not the most exciting and wonderful shiny thing, but it's a really nice applied useful example. And if any of you have been by the stand that we've got up on the street, we've been showing people today one of the virtual reality projects that we did. This was a little while ago now, but virtual reality is one of these things where everybody's very excited about, and there's lots of people doing stuff in that space. But from us, is that useful to the Met Office? Is there something we can do in the Met Office that makes use of virtual reality and enables us to do something we couldn't do before? And one of the things we did with that technology is we built an application that's used in our college for training new meteorologists. So one of the bits of the training is explaining to people how the atmosphere works, right? And a lot of that training happens by going outside and explaining what's happening right now. And that's great, but you can only train people on what's happening right now. And if you're running a week-long course, you're not going to get that much diversity within the different things you can teach people. So often you have to fall back to video footage or photos or something. But with virtual reality, we can drop our students into a scenario and show them, this is a blizzard, this is a dust storm, this is something we couldn't teach you on a sunny week in July in the UK. And that, from a technical point of view, we basically took something similar to Google Street View and added some search features where you can just look for some specific weather scenarios that the instructors want. So technically, it was a nice rough and ready prototype that we could knock together to show a real useful thing. So that's kind of give you an overview of what we do in the Infomatics Lab. But the main thing I want to talk to you about is a project we've been working on for quite a while now around big data processing and some of the challenges we have around data. So I'm sure you've heard in a lot of the other talks around our HPC capability here and what we're doing with that. But what we're doing in the Infomatics Lab is working on a suite of tools to really help people move from our science departments into making use of all of this new technology and infrastructure. So to give you an overview of the actual challenge that we're trying to solve, this is kind of the internal business challenge that we care about. We have this HPC. It's a big traditional HPC. These tend to work in kind of a batch style. So you queue up some nice big, expensive to run computationally job, and you submit it to a scheduler, and it will get queued in at some point. Some things have higher and lower priority. The weather forecast is higher priority than my random bit of research that I want to do on the side, right? And these things get scheduled into the machine. And that's great, but that means we end up with a workflow a bit like this. So we start up in the top corner with, I have a question, if I'm a researcher, that I want to ask about atmospheric science or whatever the domain is that I'm working on internally. And I will then run an experiment on the HPC. I'll either be part of our operational suite that's running anyway, or I'll be running my own bespoke experiment. That will produce a ton of data, and that data will go somewhere into one of our storage systems. And quite often, that storage system isn't the right place to do your analysis. So you then have to move that to another storage system. And that might be into one of our big compute clusters. That might be onto your laptop. It depends what the data is. But whatever that is, that's going to be a slow process for you. You then will write some code, probably in Python or R or whatever your preferred analytical programming language is. And that will be trying to actually write the science that's in your head into some code to be applied to that data. That will then probably give you some kind of visualization. You look at it with your eyes, and you understand it as an expert in that area, and that gives you a bit of insight and highlights a new question, and you go around this loop again. Right? But that loop might have taken you 10 days. So you've got to a new bit of insight, and we're going to go around this loop, and we're going to go around this loop, and we're going to go around this loop. And eventually, you keep going around this loop until that bit of insight is so profound that you can write a paper about it, and you can publish, and that is fantastic from an academic point of view. But it's taken you a very long time to get there, and there's been a lot of context switching in terms of you being able to ask questions of the data. And the volume of the data that the machines that we have are producing is just growing and growing. And these are some numbers that one of my colleagues at NCAR, which is one of our American counterparts, sent through to me, and the rate in which the data that we're producing is growing. And it's just becoming less and less feasible for us to be able to shuffle this data around quite as efficiently. And so I wanted to just give you an example that, again, one of my colleagues at NCAR sent me of where they've taken a big data set that they struggle to work with and found some interesting insight from it. So this is an ensemble field of data. This is a bunch of weather simulations that have been run. The final output data of all of these simulations is 5 terabytes. So in order for my colleague at NCAR to work with this, he has to choose. He can't move that. He hasn't got 5 terabytes of capacity wherever he is, if he's working on his desktop or if he's working on a cluster. He, as an individual, may or may not be able to store all that data. And he certainly can't load it all into memory on his machine and do some analysis on it. So he has to make decisions about what data he wants to choose. He has to extract pieces of the data and start working on it. And so he only ever sees this data set in bits and pieces, slices through that data. But we have been working as part of this, an international collaboration called Pangeo. And Pangeo it's a bit of a broad term, and it covers a lot of things. But at the heart of it, it is a collaboration between a group of academic institutions who really care about solving this problem. And I'll tell you more about kind of the actual details of that in a second. But the problem that Joe was struggling to work with, he loaded this data up using Pangeo, right? This suite of tools. He knows how to use these tools. He works on them. He loaded up the data set. And because these tools allowed him to look at the whole thing in its entirety, he decided to do an operation he couldn't do before. And that was to calculate something called the inner ensemble range, right? So this is just calculating what is the uncertainty, the variance within potential different futures that we've simulated. I won't go into detail about what that is, partly because I don't understand. I'm a techie. But what he ended up with is this plot. And this plot is just showing kind of spread of uncertainty between different ensemble members in a simulation. And what you would expect to see in this is high altitude, mountain ranges and things, there's going to be more uncertainty because the weather's more variable compared to kind of sea level. And you can kind of see that. This is of the North America. And you can see kind of the mountain ranges down the west coast. But you can see a few interesting features here. There's a funny little circle here. There's kind of another one here, another splotch there. And these don't really line up with the geographic properties of the country. These are artifacts within the data. And so they actually went back to the original data set and had a look and realized that there was a faulty sensor that was sending bad data into the original observation set that was used to produce all of this data. But this artifact was so subtle and so slight that the only way they actually realized that it was there was by comparing the entire data set to all of the entire data set. So this was just a piece of science and a piece of interesting insight that he discovered completely by accident. And science is a creative pursuit, and so we can't constraining ourselves to looking for things in the places that we expect to find them means that we're not going to come across interesting new bits of science. We're only going to find what we expect to find. So by providing people better tools, we can allow them to do more kind of exploratory, more kind of creative science. So Pangeo itself is designed to foster collaboration between multiple centers. It's about lots of institutions like the Met Office being part of solving this problem, but not owning the problem, because often you end up constraining it to your exact scenario. So we want to be a big, open, collaborative community within the scientific, particularly scientific Python ecosystem. we also didn't necessarily want to produce like new software. Pangeo isn't like a piece of software that you install. It is a whole collection of other pieces of open source software that we're contributing to and working on making interoperable and allowing it to work together, because there's so many different facets to the tools that we use, so many different pieces of tools. We need to, rather than trying to replace any of them, we just need to make them be friends, basically. And that is to eventually get to this world of dealing with the current petascale and the future exascale HPC systems that we have. So, we are one of many members of this community. Some of the people in this community are other academic institutions like us. There's NCAR and NASA and USGS and a bunch of other scientific communities. But then there's also vendors in there who are bringing the technology along that allows us to build the things that we need to build. So I'm going to dip a bit into the actual technologies that we use to make up Pangeo and allow us to take a 5 terabyte data set and calculate that inner ensemble range in, I think it took 2 or 3 minutes to do that calculation. And so kind of a high-level overview of this is that we have a lot of data that we are storing somewhere. It's generally over there from where we are sat now. But we have a big archive with lots of data in. We also have lots of compute. Other people, like Amazon, have lots of compute in their data centers. But the data's here, right? So we need to try and keep these things as close as we can to reduce that impact. So what we want to do is build distributed kind of computation engines using tools like Dask, Xarray. There's a bunch of others in there, Iris and Spark and all sorts of things, packages that can run big distributed computations across big data sets. And we want to keep those as close as we can to each other to try and keep that as fast as possible. But we then want to expose this to people in a way that's simple and minimal and has very little requirements on their end. So we don't want these people, in order to make use of a giant HPC compute system, to have some very expensive, very powerful workstation. We want them to be completely decoupled from that big data processing. So one of our preferred interfaces into Pangeo is using something called Jupyter Notebooks, which, if you've come across these there, it's a bit like a Google Doc, but for writing Python in. And you have cells, and you can write some Python code, which will be executed. You can write some text and make some notes. And it's really good from an academic and scientific point of view, because you can work your way through your analysis, doing actual computation and science and research. But the nice thing about Jupyter is that it's decoupled. It's a browser-based application like Google Docs, and all the fancy stuff is happening on a server somewhere, and all you're seeing is kind of the interface to it. So I can sit with a basic laptop and a basic internet connection, and I can connect into some server that's running my session and firing off these nice big data jobs. So there's a whole ecosystem of Python software that this has kind of been built on. And this is a slide that comes out quite a lot in SciPy and other kind of scientific Python conferences to show the hierarchy of abstraction. So each layer in this graph is getting more and more specialized. At the bottom, we've got Python. Above that, we've got tools for doing array maths and fast computation maths, and Jupyter, which is providing this nice interface. On top of that, we've then got a bunch of tools which are more around, this one's for, one is for dealing with tables, and one is for dealing with grids of data, one is for doing some machine learning pieces, one is for doing some bits of linear algebra, right? These are all kind of more specialized mathematical tools, but they're not yet into a science domain. And then this top layer is actual domain-specific tools, right? So there's Iris here, which is one of our tools that we look after in the Met Office, which is for dealing with multi-dimensional weather fields. There's CartoPy, which is good at dealing with maps. There's TensorFlow, which is even more high-level machine learning library. There's lots of other stuff that gets added to this. There's like SunPy, which is used in astronomy. And there's all sorts of these kind of domain-specific libraries, but they're built on top of the maths libraries, which are built on top of the technical engineering libraries, which are built on top of all this infrastructure. So it's really nice doing it in this way, because if I come along and I find a bug in NumPy and I fix it for the whole community. I don't just fix it for me and my weather domain, right? And this really allows us to collaborate and move quickly. And this is what a lot of the effort goes into within the Pangeo community, is making all of these tools better and making them work together. And then for us in our own specific domains, we can build our own packages on top of this and get a whole load of kind of brilliance from other people. So this is a quick video to talk you through kind of what it's like to use Pangeo. So we have a Pangeo set up. Sadly, you have to be whitelisted if you want access, but we go on, we log in with some kind of authentication, right? At the moment, we're using GitHub. And this has dropped us into Jupyter, and you can create your notebooks. Sorry, this might be a bit small, but I'm just trying to give you an overview of the process. So in this top cell, I can write some Python code, and it printed out hello world. In terms of loading the data, we make a lot of data available. We've got a bunch of data through our APIs. We've got some data that we've made available through AWS Earth. And if you're running a Pangeo platform somewhere, you can come and just load our data in that we've made publicly available. You don't have to download it. You can just load it. You just end up loading the metadata, and you can access these very large data sets without having to restore it yourself, because we're already storing it for you. And this is using Iris, which understands our weather data specifically, and will load it and allow you to work with it. And then you can produce plots and things. So this is showing wind field that has been loaded directly from our archive without having to download anything anywhere. This could be running on your laptop or whatever. So there's a whole bunch of data sets that are available through AWS Earth at the moment. The latest one that we've made available started around the beginning of the year. And this is a subset of our operational forecast system. Right? This is about 7 terabytes of data per day being pushed into S3 and made available to people to use for doing their research. So if you're interested in that, go and have a look on the AWS Earth website and search for Met Office on there. In order to actually, 7 terabytes is hard to deal with. So you can come into a tool like this. This is an example of creating a cluster. So within a cloud provider like Amazon, we can go in and we can say, I want a new compute cluster to run across my data, and I want it to have 30 cores. And it will create me that resource in a couple of lines of Python. I can then load in my weather data. The weather data understands parallelism and distribution because of these libraries we've been working on. There's one called Dask specifically, which is to do with abstracting away these kind of fields of numbers and turning them into lots of calculations that can happen in parallel. And then when we run our analysis, whatever that is, calculating the mean or doing something way more fancy that I don't understand, it boils that down into a whole list of functions that can be distributed across a cluster. And on the right-hand side, it was showing a time series of that going on. And eventually, a plot can come out the end. And the final piece that we want to get to with this is once you've done your analysis, once you've done your interesting piece of science, you want to share that with somebody. You want to be able to publish it. And so we're at a point where you can make dashboards, and you can show people some weather data, and all the code has been hidden away, and they can kind of move around. But we'd really like, from a science point of view, to get to the point where you write all your analysis in a notebook, and then you just click publish to scientific journal, and everything just gets moved, sent to a scientific journal, right? And it's got all of your analysis, it's got all of your thoughts, it's got all of your code, everything is captured nicely. Somebody else can pick that up and rerun it on top of our open data sets. So a really key piece to this is that it's a collection of tools, and you can come along with your own preferences and your own vendor kind of choices and all sorts of things, and you can build your own. So here's just a few different configurations that you might have. So on the left is one of NCAR's configurations. They've got a nice HPC called Cheyenne, and they might use Slurm to schedule on it. They like Jupyter and Xarray and NumPy, and they store all their data in HDF. That's great. We could come along, somebody else could come along and use Google Cloud if they preferred, and use the Kubernetes scheduler instead. They might not like interactive jobs. They might prefer their batch, and so they can use that, and they can choose some different tools. And this is not the whole picture, but it's to demonstrate that it's a very flexible ecosystem, and you can pop in different layers. So in our group in the Infomatics lab, we particularly run a load of stuff with Amazon Web Services at the bottom, Kubernetes above that, Jupyter, Iris, Dask, and we store everything more these days in some new cloud-optimized storage formats, but we also use a lot of HDF. There's a bunch of Pangeo deployments already out in the wild that are being used in all sorts of other institutions other than us. So NASA have got it running on their Pleiades HPC. NCAR have got it running on Cheyenne. And we've seen examples of this being run on the 3 major cloud vendors. So although we've invested a lot of time in making sure that it works on AWS, because that is our choice, because our other partners are involved, it means that more people can come and play in this space. So to just recap all of that in a nutshell, Pangeo is a big stack of Python software that's completely open source. Anybody can come along. You can pick and choose which pieces you want to use. If you're in that world, you might be using bits of these software already. We had a conversation a while back within the Met Office saying, oh, we should start using Pangeo, and people were apprehensive whenever somebody pops up saying we should use a new piece of software. But when we actually looked into it, a lot of our scientists were already using 80% of the pieces of software already, because it is a collection of these tools. And it's all about the interoperability is where we really put this effort. We're making a big effort to make our data available to people, and we're doing a lot of research now into doing that in a cloud-optimized and cloud-native way with new file formats. And then building our data sets in kind of a self-describing way where you can work with a high-level object. You don't have to worry about the hundreds of thousands of files that we will fire hose at you every day. Instead, you just worry about a high-level abstracted object, like today's weather forecast is like a single entity, and you can work with that kind of at a metadata level. And then when you want to do an operation, that operation will be scaled and run appropriately across the data. So yeah, as I said, we have some data available. This is a picture of our AWS Earth page. Please go and check this out. This is on registry.opendata.aws. We really want people to start using this data and giving us feedback on how it is useful for the research that you're doing within your different organizations. So the last thing I want to talk about is it's great for us to build these tools, and it's great for us to make these tools available internally. But we also work with, particularly with small and medium enterprises in Devon, to help them get started with using our data or tackling their own big data problems if we've got tools that will be helpful. And so there's a group called the Environmental Futures and Big Data Impact Lab, which I and a bunch of colleagues are part of, which is a collaboration between 7 partners, all have a big presence in Devon. And we all have different areas of expertise, whether it's weather or whether it's agriculture or whether it's 3D printing or machine learning. And we can help different businesses. So if that appeals to you or you know people that may find this interesting, please come and speak to us about the Impact Lab. But this is the kind of thing where it's great for us to do a lot of weather stuff and weather data-based stuff, but we want to then take that and apply that to solving business impacts, right, and actually helping people. So one example I was working on the other day, this is a fictional example, but I was working on like, what would it be like for me if I was a ferry operator, a small ferry operator, crossing a river, right? The weather is a big driver in that business. It's going to affect me if there are severe winds and high tides. I'm not going to be able to run my ferry across this river. And I'm going to have to make some kind of judgment call at some point about when I close the ferry in a high wind scenario, right? So they want they have a very tangible impact based on the data that we're producing. And so normally, you just look at the weather forecast and see high winds, and you have to make kind of a gut decision. And often, that gut decision is, how much do I trust what the Met Office is telling me? And that we would prefer people not to think about things that way. So one thing we can do with providing people all of the data that we produce is instead you can produce a plot like this. So each one of these lines in this plot is one of the futures that we've simulated. And there's a whole spread of different futures. And you can use this to produce something like a 90th percentile. This is this black dotted line. So we're saying there's a 90% chance that it's going to stay below this line, and a 10% chance we're going to go above it. And this red line is my, ferry's going to fall over line. And what we want to do is close the ferry before the weather crosses that line. And being able to take this really big, hard to deal with probabilistic data set, we can make a far more informed and useful decision about at what point I want to close my ferry. So that was kind of Pangeo in a nutshell. I appreciate that was very fast. If you have any questions, please ask me now. Come and find us at the booth. Go to pangeo.io and ask us questions on there.